preparing to live stream the webinar.
I can see the stream started. Hello everybody and welcome to the October Gophers. Probably should have put something a bit spooky on to wear, but we thought all got our traditional yellow shirts on, so you know who we are. So we got a really good, it's a slightly different format this time. We've got a really great talk for you. But just first, we'd like to mention our sponsors, Tech.io and JFrog, and also GoBridge as well. They're amazing. Amazing people to help in the community, and they definitely really help us. More on that later. Okay, and next slide, please. So we have, as I say, a slightly different format for you tonight. That we have a single talk, but it's a really good one, so we kind of wanted to focus on this one. And that is coming up now with Bill Kennedy talking about generics draft proposal review. And then later on, we're going to have some closing words as well. Next slide, please. A shout out as usual that we'd really love new speakers as well. And it doesn't matter if you've not had any experience at all speaking. You have a couple of types of slots to look at. Either a lightning talk, which is roughly 10 minutes, or a regular talk, which is around about 30 minutes or maximum of 30 minutes. As I say, if you've never spoken at a meetup or anything, there's absolutely no problem at all. There's loads of support for you, and we can kind of work up an idea. If you've had a rough idea, or even if you haven't got an idea but just want to speak, you know, you can give us a shout and we can help with that. And next slide. So some talk ideas you might want to think about is a hello world, how functions work, how methods work, or what they are, what's the difference between them. The go-to draft designs, that's cool. Using context, that's really good. Why and how to use GoList, understanding scopes, and concurrency 101. Concurrency is one of the core features of Go, obviously, ability to program concurrently really well. But I think there's tons of stuff that we can talk about to kind of explain it to each other and help that understanding. Next slide. And just a reminder, you found us anyway on Meetup, so you know that we're on Meetup. We're on Slack, and that's at invite.slack.golangbridge.org. And the channel we're in is #London. And we're also on YouTube at /London Gophers. But some of you are watching on YouTube, so you presumably found us on YouTube as well. But there are presence. We've got our regular raffle running, and that's to win JetBrains ID licenses, which is a really good prize. So all you've got to do is go to gophers.london/raffle and enter the code SPOOKY, and you'll be entered into a draw to win JetBrains licenses. So really awesome prize there. And our sponsor as well, JFrog, has some JFrog shirts. So if you'd like to really, really quickly take a picture or scan that QR code, it'll appear later on. So if you miss it this time, it'll come around. Or you can go to bit.ly or bit.ly/LondonGo JFrog t-shirts, and they should hook you up with some shirts. So no more words from me for now. I'd just like to introduce a really special guest, Bill Kennedy, who's talking about the generics draft proposal review. So over to you, Bill.
Awesome, thank you. Actually, what I want to do is show myself first here. So let me see if I can stop a share, and let's see if we can get my video pinned. I think that just worked. Brilliant. Hey, it's great to see everybody. I know it's the evening. I know you got other things to do, but you're going to hang out with me for an hour and a half. Woo, we're going to do this. All right, so we're going to talk about the current draft proposal for generics that can potentially land maybe in the August release of next year, though if I was a betting man and whiskey was on the line, I would say probably more like the February release of 22, which would make it what, 118. That's my best guess, but potentially 117. I mean, it could happen. So we're going to be, what I'm going to do here over the next hour and a little bit is share with you what the current syntax proposal looks like. I'll give you my thoughts throughout it. And then what we'll do is I can take some questions and stuff at the end. I won't be able to take questions during it. I'm going to be blind as I'm presenting the material. But I don't want to just show you what we have here in terms of syntax. I want to also show or explain why we need a new syntax. So we'll go through and do that. Okay, and time always being against us, let me share this screen now. The organizers have dropped some links around. So you should have a link to this GitHub repo. There it is, Arden Labs /Go training, all the way to the generics section. This is where the material is that I'm going to be sharing with you tonight. Now, there's 13 examples here. I can't possibly get through all of that in an hour. So we're going to be looking at the first 5. That's it. The first 5, that's my goal, to get through that fairly quickly. I'm going to talk a little fast as well to make sure I can get through that material. And if I show you the first 5 examples, you really will have seen 80 to 85% of the draft proposal and what's new. Now, on the README in the GitHub repo here, we do have links here that will take you to the draft document, which is another link that I provided the organizers to share with you. You can see this was updated last in September. I think at this point, however, the syntax that I'm going to be showing you isn't going to be changing much. They're actually, as of a couple of weeks ago, starting to prototype some ideas in the compiler. But what I'm showing you right now isn't part of the compiler yet. This is purely a draft syntax proposal. And in order to play with it, they've given us a tool called Go2Go. Now there is a Go2Go playground that will allow you to experiment and prototype using the new syntax. It's a transpiler at the end of the day, and that's what we're going to be using locally on my machine. And I don't know when we can expect any even branch of Go to have a functioning compiler leveraging this syntax just yet. So this is just a transpiler, and do not start to use this in your production code. I've had people say, oh, Bill, can I start using this? The answer is no. I'm telling you, don't start using this just yet. Okay. There's a high-level overview here of what is expected to be in the first release. Notice that there's going to be multiple releases of generics over the course of a few years. This is just the first release. I think this list is fairly locked in as well, especially if we're looking at the end of August or August next year, February. I don't have to read this. You can read it. And these are some of the things, or most of the things I'll be talking about tonight. This is a list of omissions. It doesn't mean it's omitted for the lifetime of the language. It just means it's not really being focused on right now as part of the first release of generics in Go. There may be some things here that you're bummed out about, like metaprogramming and some other things. I just need you to be aware that what the big focus is right now is a syntax that looks and feels like Go, and a syntax that allows us to continue to write code that we can read and comprehend, and we'll talk about that in the talk. There are extra blog posts, ones that I've been writing about the examples, others from the community, and I am running the tool locally, the Go2Go tool locally. The instructions for you wanting to do that is right here. And so you'll see here, if I type Go version, I'm running a version that is built from changes as of yesterday. So I'm not using the 1.15.3 compiler. I'm using one that I've built from source here. So it has the Go2Go tooling. All right, enough about that. Time is against us. It is roughly 15 minutes after the hour. So about an hour from now, I should be done with going through all this stuff. And then we can figure out how to maybe take some questions, get some feedback. We're going to start this first example right here. We're going to spend a little bit of time here because this is where we're going to look at and start to see the new syntax at play. And before I do that, what I really want to do is kind of walk through what we can do today in Go, what's working today, what's maybe not working today, and then where generics potentially fits in. Now, what's critically important here is this entire conversation tonight is not going to be about using generics to get better performance in your code. In fact, we have zero clue right now if that's even possible because we do not have a compiler implementation, and we won't for some time. We can talk a little bit about the options that the language team has with compiler implementations at the end of the talk and how that may or may not. So what we're going to focus on is our ability to read and comprehend the code we're writing as it relates to what we can do today and generics. And I'm going to start off right here with these two functions, and I'm going to call these functions a concrete function. And the reason I call these concrete functions is because they are functions that accept concrete data based on what that data is. So they're limited to just one type of data. And this function called print numbers here accepts a slice of int, a collection of integers, and only a collection of integers. Just like on line 21, this print function accepts a slice of string, a collection of strings. These are concrete functions asking for data based on what it is. Now, if you look at the implementation of the print numbers function here on these 5 lines of code, right? We're using 2 print statements, headers, and carriage return line feeds, and then we're doing a linear traversal using our 4 range mechanics, and you can see another print in there, right? This function is coded using our language syntax and mechanics because the data that we're working with is this concrete collection, right? And I'm going to make a bold statement here that I believe that every Go developer, even if you're only a few days in, can read and comprehend what this code is doing, right? Even if you've never looked at Go syntax before, if you've programmed before, I think you could look at this and very quickly get a good sense of what this code is doing, right? And this is what we want to achieve. This is why we love Go, because it comes with this high level of readability and code comprehension. Okay, great. So we see these 5 lines of code that we've written to print out every individual integer in the collection. And if I wanted to do that with a collection of strings, you can see that it's really the same 5 lines of code. The only difference is the variable names have changed just to have context. But if we've had the highest level of readability we can achieve here, we've got the same high level of readability here, right? And if I wanted to do this with floats, if I wanted to do this with users and customers or any other entity, well, I can copy the same 5 lines of code and we can keep doing that. Now, the nice thing about having another function and another function and another function might be that we are maintaining high levels of readability for all the code we're writing. But there's a trade-off here that I want to focus on, and that's maintainability, right? Right now, at some point, if we had 5 or 6 versions of this function for different concrete pieces of data, we could be talking about 25, 30, 35 lines of code that we're now maintaining. And so even though we're going to have these high levels of readability, the maintainability starts to drop. And what we need to do as software developers, what we're trying to do all the time, is balance that readability with the maintainability, right? And so when I look at this problem, this maintainability problem that I have here, as I want to use floats, users, and customers, and anything else, I start to ask myself, well, in the current version of Go that we have today, is there a way to maintain this high level of readability by using my language syntax and mechanics, but to get back some maintainability if I want to do this across multiple concrete types? Now, my first thought is, well, we could use a polymorphic function and then leverage type assertions in the language to maybe balance out the maintainability of this functionality. Now, on line 35, I'm calling this a polymorphic function because it's accepting data now through the use of an interface type, which means it's accepting data not based on what it is, but based on what it can do. That's what makes this polymorphic. We're going to call this runtime polymorphism. Polymorphism meaning that a piece of code changes its behavior depending upon the concrete data it is operating on. And the concrete data in the case here has to exhibit the full method set of behavior defined by the interface. But what's interesting here is we don't necessarily need the concrete data to behave in any way. In fact, that would get in our way. So Go has what's called the empty interface, which allows us to write a polymorphic function that has no constraint or restriction on behavior. And it's going to allow us to write in a sense, a generic function that can accept any piece of concrete data. Now, that sounds fantastic, but the problem here is that the empty interface tells us nothing about the concrete data, so we're blind. And this is where the type assertion comes in. And so this polymorphic function, at that point, is going to allow us to pass our slice of int, our slice of string, our slice of float, our slice of whatever. But on line 37, you can see me performing a generic type assertion, asking the question, what is inside, what concrete data exists inside of V? And then using case statements for the conditional logic. If it's a slice of int, execute this code. If it's a slice of string, execute this code. And so what I've kind of done here is consolidated at least the 2 functions that I had into one and reduce the amount of code duplication basically from another 5 lines of code, maybe down to 3. And I would gain benefit if we continue to add case statements here. That being said, these 3 lines of code are really the same again. We're using our language mechanics and syntax, so we're getting that high level of readability. But, and though maybe we've helped a little bit with maintainability, I mean, this isn't a generic function, right? If I pass a slice of float into this function today, we ain't going to see anything. this function would still continue to require us to add code to it, code that is fairly the same, even though it's been reduced. So maybe we're talking, instead of 25 lines of code for 5 types, we're not talking maybe an extra 15 lines of code. But I mean, it's gotten us closer to the balance of readability and maintainability. So then I ask myself, well, what would really be nice maybe is to really write a generic version of this print function in Go. Can I do that today? And the answer ends up being, yeah, I can. Here it is. Now, I got to write another polymorphic function. I've got to use the empty interface again, because I got to be able to accept concrete data of any type, regardless of its behavior. However, something interesting happens here. This is a fully generic function. It's requiring 8 lines of code to do the same thing that was taking us 5 lines of code when we were working with our concrete function. But the thing is that I can't make the same statement that this function has that high level of readability and code comprehension anymore. That developers, even those only a few days into the language, can reason what this is, can look at it and right. And why? It's primarily because we're not using our language syntax and mechanics anymore. We're actually using an API. And if you don't know this API, then you can't quickly comprehend what's going on in this code. And even though we're going to get better maintainability now, 8 lines of code to do it all, our readability drops. And if we were to look at how this code works, we've got to use the reflect package, which I love. I love the reflect package. I think it's a powerful package. I never want to get rid of it. There's real value in it. However, when we look at it here, I've got to reflect over the concrete data stored inside of V. And now at runtime, I've got to ask questions like, was a slice passed in as the concrete data? Because if it's not, well, then we're done. And there's no way to prevent that at compile time. So this is all at runtime, right? And then to perform a linear traversal, I can't use my for range mechanics. Again, I've got to use a method named len and then build my for I there. You see that. And then to perform the linear traversal, I need another method passing an I, and then I need this interface to get back to the data, and then I can print it. And so I can walk through this code with you, and you can all go, okay, yeah, I get it. But it wasn't obvious at first sight, like the first 5 lines of code that I shared with you. So we're gaining maintainability here, but I think we're losing some readability. And by the way, I'm getting lucky in all these examples because the print function is capable of printing a value, of printing something, an output for any concrete value, because it's using reflection underneath to be generic as well. Okay, so I go back now and I say to myself, how nice would it be to be able to write a function like this where I can maintain the highest level of readability that I started with those 5 lines of code, but also get the high levels of maintainability that I'm kind of getting here with the reflect. I want both. I'm going to be greedy. In order to get both, I have to essentially write a concrete function that lets me use my language syntax and mechanics, but to be able to just do that code once. And this is where generics is going to come in. What generics is going to do is let us write concrete functions that are also polymorphic, but not runtime polymorphism, compile time polymorphism. And this is where we're going to be able to get that high level of readability and the high level of maintainability. Now, before we break down some of the new syntax, look at the 5 lines of code that this generic function is using. It is the same 5 lines of code we started with. It is our language syntax and mechanics, which means that this code should have the same high level of readability and code comprehension that we started with. But there's a few things here that we need that have to be newly introduced into the language in order to make this work. And what I'm going to do is remove what is currently new and just focus on this function as if that stuff didn't exist for a second. Now look, all of you can look on line 81 and see this function and have a general understanding of what I'm trying to do here, right? What I'm trying to say is I'd like this function print to accept a slice of not t, but of some type t to be determined later, but t being a concrete type. And that's the win, because if t ends up being a concrete type, then I can use my language syntax and mechanics against this slice of some type t. And it would be brilliant if this is all we had to do. But the problem with this syntax is that there is backwards compatibility problems with it, right? This is how we write functions today. This syntax is expecting that at some point before we hit build, right, that I or someone else does something similar to this in some source code file related to this particular package. But that's not what we want. The point is that we're not going to declare t before we hit build. The idea is that t represents some type to be determined later, either determined by the compiler compile time or explicitly defined by us, but to be determined later. So here's the problem. We need a new syntax that tells the compiler that t is a generic type to be determined later. And don't expect to find a declaration, because you're not going to find one. So after years of looking at choices and after months of the new draft proposal, this is the syntax that got flushed out. And it's a use of square brackets bound to the function name, where we can list type identifiers that are going to be considered generic types for this function. And so what that syntax right now is saying is that t is a generic type to be determined later. Don't go looking for a declaration. You're not going to find it. We've got to determine what this is later, but it's concrete. And so let's just write code as if it's already an int or a string or whatever that type is. Now, this looks like an array, doesn't it? And there's an array syntax that we have around the use of square brackets. So in order to simplify things and make sure there's no confusion, the draft says that every type identifier, whether it's individual or a list of identifiers that you might have in this set of square brackets, needs to have what is called a constraint. Now, I'm going to talk about constraints at the last two examples. But when there isn't any constraint, when t can be anything, when t can be substituted for any type because there is no constraint on what t needs to be, there is a pre-declared constraint named any. And that's what we're going to use. So moving forward right now until I get to the last two examples, every time I declare a list of type identifiers that are going to represent generic types, in this case for this function, you're going to see the use of any, because I got to apply this sort of constraint that we're going to get into in a little bit. There's the new syntax. This is why we need it, because the compiler needs to be told that t is going to be a generic type. And we're going to do it with this new syntax right in here. And now we get to write that code as if t was an int, t was a string, t was a user, t was any form of an entity. Brilliant. Now, let's explore this a little bit more. Here in main, I've constructed a slice of integers on line 92 and a slice of strings on line 98. And I've passed that slice to 4 functions and the slice of strings to 4 functions that can accept, knowing that these 2 functions, print, reflect, and print, are generic functions. Now, if I want to run this code, it has to be transpiled first because we don't have a compiler implementation yet. But I can come out here to my terminal window. Oops, try it again. And what we can do is you can see the source code file there for .go2. And what I can do is use this version of Go that I have that I built from source, because it has a tool called Go2Go, which is the transpiler. I could tell it to run and I can give it the go to source code file. What it will do is transpile that go-to file into a Go source code file with special functionality built in that can then be built and run. And you can see here that we've got the same output regardless of the functions that we're using, including our generic functions. Now, the real win here is this, right? The whole idea is I can do something like this, change this to a collection of floating point numbers. I don't have to implement anything new. And as we're already aware, our reflect implementation and our generic implementation should be able to accept this slice of floats, and it does, and we see the output. This is what we're going after, right? But also with the idea that we now have a function that has that highest level of readability and code comprehension and that highest level of maintainability. We're getting both here. And now if I want to pass anything new to it, I can. Now, a couple other things here that are important. I said that T to be determined later, right? A slice of some type T to be determined later. So how is that done? There's two ways that we can determine T later. One way, and a way that keeps our code maybe cleaner, is the compiler's ability to infer the type. And this is when we say to be determined at compile time, where the compiler attempts to determine T, infer what T is. Now, in this case, the compiler is doing just that. It's inferring that T is an int when I pass numbers, or T is a float 64 when I pass floats. And it's capable of doing that because we're using the generic type identifier as part of an input parameter. And so the compiler can see what we're passing for that input and then make the inference that, oh, T is an int, T is a float, T is a string. But there may be times where the generic type isn't being used as part of the input. Maybe it's only being used as the output. Maybe it's being used somehow in the implementation of the function. There are going to be times where the compiler just cannot infer the type at compile time, but it still has to be determined later. In these particular cases, you have the ability to pass the type information in just like you pass data into the function. In this case, to be determined later means that you explicitly pass the type information in this case, at the call site. And in these cases, now the compiler will leverage what you're explicitly stating and then be able to perform all those compiler checks that it would continue to do. And so though we love the idea of inferring the type at compile time because that function call looks and feels like any other function call in Go, you might be leveraging generic types in a way where it cannot be inferred. And then you have the ability to explicitly pass that information in this case, at the call site, at a construction site, wherever that needs to be done. Okay. So we've seen our first form of generics here. We now understand why we need this syntax. We need it to maintain backwards compatibility with our existing language syntax and to tell the compiler that T is a generic type to be determined later, either at compile time or explicitly. Now, if we're writing any sort of real world programs, we're going to be defining our own data structures, right? A big part of everything that we do in code revolves around data. And this is why I teach so much that Go is a data-oriented programming language. If you don't understand the data, you don't understand the problem. You don't understand the problem, how can you even begin to write code? It's the data structures that represent the problem. And if the data structures are right, then the algorithms tend to become self-evident, and those algorithms being data transformations. So generics needs to also not just flow into the declaration of functions, but we're going to have types as well that might need some aspects of generics. Now, there's two ways of declaring a user-defined type in Go. One is through the use of an underlying type, and then one is through the use of the keyword struct. Let's kind of explore both paths here so we can get an understanding of how we can use generics with our data structures. Now, we're going to walk through a very similar exercise as we just performed. Let's say that I wanted or needed this vector of integers. Well, I can do exactly what I did on line 15 here. I can declare a user-defined type vector int, and I can say that it is based on this underlying type, which is a slice event. You see me doing the same thing here on line 24, where I needed a vector string. Remember, these are concrete types, right? Again, that vector int can only work with int. That vector string can only work with string. That's actually a good thing, not necessarily a bad thing, as we'll see. But to make this example a little bit more interesting, I've added a method named last to both of these types. Now, the idea of last is to return the value at the highest index position currently in the vector and return a value of that vector's type, which means last returns an int here, last returns a string. But look at the code, right? It's the same 4 lines of code again, regardless of working with integers and or strings. We have to check to see if the vector is empty. If it is, we return the 0 value literal for int. That's an idiom or guideline that we follow in Go, and then an error. Or we can return the value at the largest index position and the 0 value literal nil for the interface error. If you look at last for the string, check if it's empty. The only real difference is I'm not passing 0, I'm passing an empty string because that's what the 0 value is of a string, and everything else is the same. And again, if I wanted to do this with floats and users, and you get it, we're there already. Lots of code, high levels of readability, high levels of code comprehension, maintainability starting to wither away over time as more types are introduced. So we go back to, is it possible to implement these semantics in a generic way today in Go? And actually, I'm going to say, no, there isn't, for a couple of reasons. If you see here on line 40, I'm using the empty interface now for my vector. Now, what that means here is I can store concrete data in this vector, right? Again, determined at runtime. Any concrete piece of data, as long as it exhibits the full method set of behavior, there is no behavior. The reason I'm saying this really isn't the same semantics, and a problem that's introduced here, is that this vector isn't tied to a single piece of data. I could put integers and strings and floats and users and customers all in the same vector, and you might think, well, that's powerful. It may be powerful, but it creates a usability issue. Look at the call to last. What is last returning? It's returning the empty interface, which means that when the caller calls last and they get back the concrete data already decoupled in the empty interface, they're blind. Do they have an int? Do they have a string? Do they have a user? Do you have a customer? And the very next time you call last, there's no guarantee it's the same data type. And so, though we're looking at code here that is fairly identical in terms of implementation and therefore maybe readability and code comprehension, usability in this case, because we're returning or using the empty interface on the return, creates this usability issue again. Okay, so what about leveraging new generics syntax to implement a vector? Well, this again will give us the best of both worlds. It will give us the high level of readability and code comprehension. It will allow the vector to work with a single data type, which brings our usability back. And then again, we got our maintainability. I only have to write these 5 lines of code once. Now, throughout the talk, you're going to see me doing this, because I think it's important. Our brains are right now wired to look at Go syntax the way we see it today. So I want to introduce the new syntax as needed. You know what I'm trying to do on line 56. I'm trying to say that I want a type name vector that is based on an underlying type of some slice T to be determined later. As soon as I say T to be determined later, what do we know? We know I've got to do this, because this is the new syntax that allows us to represent to the compiler that T is not a type that's going to be declared before we compile. T is a type to be determined later. So boom. Remember, we did this with the function. We put the syntax on the right-hand side of the function name. Now you're seeing us do it on the right-hand side of the type's name. We now have this generic type vector that represents a slice of some type T to be determined later. Now look at the implementation of last. Look at the receiver. This is a value receiver, right? We're using value semantics. But notice that it can't just be vector, because vector in and of itself doesn't have enough meaning. There's not enough type information being represented. A vector is only good as the concrete type T that we're substituting. Since we do not know what T needs to be just yet, like when we're implementing a method, we're going to use the square brackets against the type name to represent a vector of some type T. Notice that when it comes to methods, we're not doing this like we are with functions. I don't need to do that because that syntax is already applied to the type that we are now a method for. So when it comes to that receiver, or anytime we're going to mention vector, in this particular case, it's vector sub T, vector of some type T, that's the receiver. Now look at the return. The return is also a value of some type T. That's great, right? That's getting rid of the empty interface. That should bring our usability back, since that could become an int or a string or a float or whatever that is. Now, there is some other little interesting things in the implementation. Look, we're going to check if that underlying slice is empty. Notice that I am using language, syntax, and mechanics. I'm using the built-in function lane. I'm doing these things. This is beautiful. If it's not empty, I return a value of that type T in the highest index position. Boom, there we go. Beautiful. But what if it is empty? I need to return the 0 value of that type T. Now, some of you might be looking at this right away and going, well, Bill, why can't we do that? Isn't that the construction of some type T set to its 0 value, since we're using empty literal construction? My answer to you is, yeah, if T is some sort of struct type. However, what if T is an int? Is that legal syntax? The answer is no. You see, empty literal construction isn't a valid syntax for all types in the language. What we need is a syntax that is universal regardless of what the type is. Now, today we only have two choices. There's two ways to universally construct a value of some type T to its 0 value state. The first one is what you're seeing on line 59 through the use of the keyword var, var 0t, regardless of what T is, whether it's an int, whether it's a user, or even a slice of something, that gives you 0 value. This is why in all of my classes, I push all the time to use var when you're constructing anything to its 0 value state. And you can see here that I am having to add a line of code to declare a variable named 0. And then in this particular case, we would return 0 to represent the 0 value to be returned on the error. Now, there is another way of doing this, but one of the core philosophies that I have is don't make things easy to do, make things easy to understand. Sometimes that means you got to write a little bit more code. Sometimes it means you're going to copy and paste a little bit more. Now, the built-in function new does construct values to their 0 value state, regardless of what T is. However, it uses pointer semantics and returns you the address of that newly constructed value. So the problem here now is I have to dereference the pointer, which breaks a whole bunch of other guidelines I have, which is you do not make a copy of the value that a pointer points to. That's like immediate death. And so though this syntax would eliminate a line of code, from my perspective, I'm violating two of my design guidelines. One, this isn't making the code easier to understand. Not every Go developer, even a week in, can necessarily understand what the syntax is. And for me, it's violating data semantics. And so this is something that at least I'm gonna avoid in my code bases and really try to teach against. But this would give you the other way of universally constructing a value of type T to its zero value state and getting it back. But this is what I'm pushing. And I don't know, there may be at the end of the day, something else that the language team comes up with to make this a little more comprehensible. I don't know, but that's what you're seeing here. You're seeing here the use of var and a variable named 0 to construct a value of type T to its zero value state, and it'll be returned then on line 61. Though I expect some people might, in time, to keep it at the return site, do things like this, right? There are guidelines and idioms and things that we still need to discuss and come up with over the next 12 to 18 months, and we'll all get there. But I just wanted you to appreciate what's happening there. Now, let's get back to running some of this code here so we can get a good understanding of that readability, maintainability, usability. Now, you see me here. I'm constructing my vector int, and I'm returning that integer. And because I know it's an integer, I can operate on it like really cleanly. Same thing. I can construct my vector of string, I can call last, I can operate on the value coming out of last. Remember I said the usability with the use of the empty interface starts to fall off because there's the construction. When I call last, I really don't know what concrete data I have. And now we're back to performing type assertions in order to apply specific logic to the concrete data that may or may not have come out of last. So there's that usability problem. But when it comes to our generic, a couple things here that I want to stress. If I wanted to construct my vector to work with some type int, not some type, but to work with int for some type t set to its zero value state, there it is. There's no way for the compiler to infer type information in this zero value state construction. And so here's a case where we have to, there's no way around it, be explicit to what t is going to be. There's no way to infer it. Now, what if I was going to construct the vector using literal construction? Couldn't the compiler infer the type now to be an int? Absolutely. Absolutely. If we're using literal construction, now there's information that would allow the compiler to infer the type t. Now you might be asking, Bill, why did you explicitly pass it here on line 110 when the compiler can infer it? It's mainly because the Go transpiler didn't implement this yet because it wasn't critically important to do so in the tooling, but it will be in the final version of the compiler. So I've got to explicitly pass it, not because the draft wouldn't support it, it just wasn't implemented. And I'm fine with it not being implemented in the transpiler because I want the language team to get to the real stuff. I wanted to start working on the compiler. Don't spend your time on this tool. This tool's going away. Just enough for us to experiment with it. But what's nice is what? We get back the integer, we can work with an int. We get back a string, we can work with a string. So you're seeing here how the use of generics, at least with this type, gave us that high level of readability, gave us a high level of maintainability and some usability that we weren't going to get with the empty interface. Okay, pretty cool. I can run this, it would run, you'll see it. I could copy this, start working with floats, it would work. You can see it. I'm not going to spend time doing that. Now, let's quickly talk about struct types. One of the areas that I think generics are really going to help in terms of data structures are these, what we call these container types. linked lists, stacks, right? Queues, all of these data structures today where we don't have the ability to do that generically, where we've got a lot of implementation. And the reality is, and because of time, I'm not going to go too deep here. The reality is that when you look at the implementation of a container type like a linked list, look at all the code here, right? There's 11 lines of code that I'm writing for add. If we look here, like 7 lines of this is the same regardless of what the type is, right? And we can multiply that across an entire API for a linked list. This is why everybody starts doing code generation and things like that, because the bulk of the code, some large percent, doesn't particularly care if we're constructing nodes that are working with integers or strings or not. And so this is an area where I think we're going to see some real value with this first release of generics. We'll be able to have these types of data structures implemented one for all. And when you think about the standard library today, the sync package really comes into mind, because the sync package today has a map sync.pool that's using empty interfaces. And I think it's a great opportunity to maybe leverage a generic type there and have that implementation more concrete than say runtime polymorphism. Get back to that compile time polymorph, more concrete. All right, because of time, I'm not going to go any deeper. You can look at O3. I've got a blog post that goes a little deeper in here. I want to make sure I spend the rest of the time that I have talking about constraint, because this is where something new ends up in the syntax here. And we're going to go back to looking at functions. Now, that print function that I showed you before, it was written in a way where it didn't matter what type T was substituted for, primarily also because print can provide a value for any type T. But the reality is that many of the functions we're writing won't be able to work with just any type. There is what we call constraint against what T can be, and I want to share that with you. And the first way I want to share it with you is through this idea of behavior. So look at line 13 and line 22. I've defined these two types, user-defined types, user and customer. And for each of these, I've implemented some behavior named string that returns a string. And what these methods do is stringify that entity, stringify a user, stringify a customer. Why would we ever do that? Maybe for logging, maybe for some form of marshaling. I don't know, but it's things that at least I've done in the last N number of years. And you can see I've hard-coded some JSON syntax. Now, to make this a little bit more interesting, I've created these functions called stringify, stringify a user, stringify customers. And what they do is bulk stringification, right? Given a slice of user, return a slice of string. Given a slice of customer, return that slice of string. And if you look at the 5 lines of code I've written here, we're back to our language syntax and mechanics. We're back to the built-in functions, right? Which essentially are also generic functions when you think about it. Append can take a slice of any type T and a value of that same type T and perform operations, right? But those generics are tied to the language designers. We don't get to have access to them, but we're leveraging some of that. So look at this. I construct a slice of string using the built-in function length. I use my for range mechanics so I can go over each user. But the real key here is calling the string method for the stringification. The real key here is calling the string method on line 49 for the stringification. But once again, it's the same 5 lines of code. We talked about that. I don't want to harp on that anymore. You know where we're going, right? And look, I could go back and perform asserts. I can perform asserts here. And because we're getting back to our concrete types, we know that these methods exist. We know that that's limiting. Look at this. In 13 lines of code, I can write a generic version of that stringify function. Once again, the reading comprehension of this code is not nearly where it is with those 5 lines of code, again, because we're working with an API. But if I walk through this, reflect the value, is it a slice? If not, goodbye. If it is, let's construct the new slice with the method len. Let's use I over len. This is kind of cool. Maybe you didn't know this, but at runtime, I can inspect if the value that we're indexing over has a method named string. If it doesn't, we're done. If it does, I can execute it, and then I can get back to the data and append it. So you see, this is a generic version of that bulk stringification. It's just using an API, so we've lost that readability, though we're, maybe from a maintainability, we're back down to those 13 lines of code. So guess what? I want it all. And so here we are. Isn't this really what I want to write? I want a stringify function that accepts a slice of some type T to be determined later and returns that slice of string. Using my language syntax and mechanics, just these 5 lines of code to do it all. Now, as soon as I said T needed to be a generic type, what happened? I did this, right? I said, okay, T needs to be a generic type. So let's add the brackets and let's add any constraint. And here's the problem. If I go into example 4 and run this using T any, what is the compiler telling me? It says, Bill, sorry, I cannot compile this piece of code because I don't know if a value of some type T will have that string behavior. And therefore, there's no guarantee that if I compile this, it won't blow up. At runtime, compile has to do its integrity checks. So here's a case where T can't just be anything because it has to exhibit this behavior. Now, let's think about this for a second, okay? Because behavioral constraint really isn't new in the language. Look. I could write that function, right? Again, this is a concrete function. Why is it a concrete function? Because it's accepting data based on what it is, user and user alone. All right. I could do this too, right? I could write Bill to be a polymorphic function. Now this function is saying I will accept any concrete piece of data, a user, even a customer, as long as that data exhibits the full method set of behavior defined by stringer, which is a method named string. In other words, this is polymorphic because on line 116, that line of code changes its behavior depending upon the concrete data that it's operating on. If I pass in a user, it's going to execute the user implementation, customer. That's polymorphic. It's runtime polymorphism, but the compiler can check that any data that we are going to be passing through, any concrete data we're going to be passing through, does exhibit the full method set of behavior defined by stringer. You see, the interface is technically a constraint against behavior. We can't just pass any concrete data, only that data that is constrained with the ability to exhibit the full method set of behavior defined by stringer. We have the same problem, a little bit in reverse, but we have the same problem. See, that generic function needs to substitute T. I'm calling this compile time polymorphism because this line of code will change its behavior depending upon the concrete data that we're operating on. It's still polymorphism, but it's going to be a compile time because we have to substitute what T is, a compile time, to implement a version of this function. So we have the same constraint. We need to constrain T so it can only be substituted for types whose values implement string. Now, since we already use interfaces to define constraints on behavior, what the draft says is, why don't we continue to use the interface as a mechanic to create a constraint on behavior for that type T? That's what we're doing. We're now telling the compiler, T can't be anything. So when you see somebody calling stringify, validate that the substitution and a value for that type does implement that method. And now, when we come back here, as you can see, I have some problems. I forgot to remove this. No more compiler messages. Everything builds. Because now, when the compiler sees these calls here, passing user and customer, it can validate that user and customer, implement the full method set of behavior defined by stringer. And now at compile time, we can validate that our implementation is going to be clean. Very, very, very cool. And what's nice here is that we're not introducing anything new because we're going to leverage what already exists, which are interfaces. Now, the last example introduces something new to the language. And it's because our traditional polymorphic functions don't have this particular problem that our generic functions do. And that is that sometimes the constraint that has to be applied to T is not based on a method set of behavior, but based on the ability to perform a certain operation, like adding, subtraction, division. These are operations that we can perform against some concrete data, but not all. And so we have now a need to be able to define constraint that I'm going to call against an operation, as opposed to a method set of behavior. And this is the last little example that I want to share with you tonight. And I want to start right here. Just look at my add function. I've removed a bunch of stuff. You know what I want to do. You know what I'm saying here. I'd like to write a generic function named add that accepts a value of some type T and a second value of some type T and adds them together and returns a new value of that same type T. Now we know T is a generic type, so we do this. Except what's the problem? T can't be anything. What do you mean? Why can't it not be anything, Bill? Well, we agree that T can be an int. I can add two ints together. We agree it can be a string. However, it can't be a struct type named user. Can't add struct types together. We don't have operator overloading in the language. It's not coming anytime soon. And so T can't be anything because of this situation. And in fact, if we think about it, even if I make it a string, what if I change this to subtraction? Can't subtract strings, can you? So this is interesting because T has to be constrained, but not based on a method set, based on its ability to work within the scope of this operation. And we are still responsible for providing a constraint to the compiler to make sure that any data that is passed for that type T can operate within the scope of that operation. So how do we create a constraint in a situation now where we don't have syntax for it? Exactly, we need something new. Now, the community spent a lot of time on this, and at least to date, this is the best that we've come up with. And that is to continue to leverage the interface as a way of constraining that type, but to do it with a type list. In other words, what we're now saying is T can only be substituted for these sets of types, nothing more, nothing less. Now, there's a couple of things here I want to make clear. If type Bill had an underlying type of string, it would be compliant and we could pass it in. But if this was a struct, right, it wouldn't be able to be passed in unless I did this, which means that this type list could be really fixed to just type defined in a single package, something we really don't have today, right? What's the beautiful thing about the interface? That anybody can define an interface and anybody's concrete type, regardless of where it exists, if it implements the full method set of behaviors compliant. So unless we're using these built-in types, you don't necessarily have coverage outside of types in your package. Okay, but the underlying types will work. What else? Well, this is a problem. I can't use this interface to write a traditional polymorphic function because essentially it doesn't even make sense. This is our traditional polymorphic function. It says, I will accept any concrete piece of data based on what it can do. Do. There's no do here. And so one interesting aspect to this is that we now could have interfaces that can only be applied to our generic or compile time polymorphic functions, can't be used in our runtime polymorphic functions anymore. That being said, the draft doesn't eliminate, if I can spell this right, you also adding behavior in combinations with type lists, though I haven't found any real need for this outside of maybe regulatory compliance, where you do have a set of types in your system for that package. And what you want to say is, look, this add can only be used with these types and these types only. Now that gets interesting in a regulatory environment where you don't have to worry about somebody just randomly implementing behavior, right? And then suddenly executing functionality. That gets interesting to me. But I just want you to know that you have the ability to mix this if it becomes important. I haven't found a practical reason for it yet. And nobody's really come up with a better idea for this. Remember that every type, whether it's the full list here, and you can name these things anything you want, need a constraint. So you could do something like this. Hey, Tom is any, John and Kay is add only, but you can only apply one constraint, which is why interface composition could become important here. So you can define that one interface that has all of the constraint that some generic type might need. Now, there are some ideas around having either more pre-declared type constraints like comparable, which is being played with. Comparable would allow us to conform or be constrained to make sure that a value of that type can be used in a condition statement like this. Or maybe the idea is to have a new package in the standard library with a whole set of these kind of interface constraints that are going to be very, very common. So they're all implemented once and we all don't have that kind of duplication in our code. Now, there's other interesting things in this example that I'm not going to have time to go through, but I do really want everyone to, if you're really interested in looking and learning more, to take the time to go through all of these examples slowly, and you can always reach out to me if you get stuck, because all of these will give you some better ideas also where generics can fit in. Like, how can we leverage it in having a concurrency package? Well, there's some experimentation there in channels. Is it possible to maybe replace certain APIs in the standard library without breaking backwards compatibility? That was an experiment by Roger Pepe here with the IO package. And then other things around other types of constraints and field access and some interesting things here that if you're interested that you can explore. But as it relates to what I want to show you right now, that is basically it. That is our hour. So I'm going to stop sharing for a second. There we are. I hope in that basic hour that we just spent, you've got a very kind of good, clear idea of where the syntax is, where it's new, why we need it, some of the good, some of the bad, a little bit of the ugly. But I think this is a really great place to start for Go as it relates to generics. So organizers, I'm ready to take any sort of question that I could potentially answer.
Firstly, thanks, Bill. That was incredible. Actually, personally, I've looked through this. I've looked through the review, the draft. Sorry, and I've followed the discussion. But seeing all of those things, those examples laid out end to end, has been a really good learning experience for me. So personally, thank you. There's been a little bit of discussion on the chat. I guess one kind of feeling is that how do we kind of limit the blast radius of bad uses of generics? I think there's been a little bit worried that the people, you know, kind of generally, that people might say, oh, that's really cool, I'll just start using it for every purpose. But is there any kind of sort of mitigation for people doing that?
I've got kind of two answers to this question. The first one is, I believe that the direction that the compiler implementation will go in is not to write out every single function or type for every type. And there's two reasons for that. One, that would take more compiler time. And you know that we are a community that values our compile time. But two, then if you're not going to do that, then what you need to kind of leverage is what they have today for generics as relates to make, append, len, right? And that means that for every generic function or type, there's still only going to be one implementation. That will help with compiler speed, right? But what that means to me also is that you're not going to necessarily see a performance benefit whether you use runtime or compile time polymorphism. And you know developers, if they even feel like they're going to get an extra nanosecond of time, they're going to go in that direction whether they need it or not. So one of the things I'm praying for is that when we have a working compiler here near the end of next year, and people start doing their benchmarks, because they're going to do their benchmarks, that it's all the same. And so we take performance out of the loop in terms of, are you making this decision? So then it's got to go back to readability, and it's got to go back to code comprehension for your team, right? Which is what I've been trying to stress here. Now, the other thing that I've been asking for from the team, and I'd like this to be a community effort, is that there is a decent amount of documentation published by and sanctioned from the Go team, providing design philosophy and guidelines for things like naming, when to use it, when you really shouldn't be using it. And part of the work I'm doing here is the beginnings of some of that, right? And I'm praying that with that in place, people at work who are doing code reviews and they see somebody slip in a generic function where a traditional polymorphic function could have worked, and it's silly to me that there are brilliant people working on teams who say something, I walk into a training, I say the same thing, and everybody wants to listen to me. They don't want to listen to Antonio until I say it, right? But what's going to help you and Kat and Antonio is you can point to that documentation and say, it's not me, it's the Go team saying this is not where we want to use it. And so I've talked to them about this. They're on board with doing that. And I think these two areas is where we could potentially see not what I would call part two of channels, right? How many people come into the language year one, abuse channels beyond comprehension, and realize year two, when they have to maintain it all, that they want to rip it out, right? So I think because we're 10 years in, we could reduce some of that. Now, let's get real. Why is generics even being introduced into the language whatsoever? Why am I even doing this, right? Like, let's be upfront and honest. There are large enterprise companies that have told the language team in one form or the other, we cannot use your language because we've got these big, heavy frameworks that we need to maintain. And from our perspective, whether we want to agree with them or not, we need this type of functionality in the language in order for us to maintain these large enterprise frameworks. So the language team is going, okay, let's get this syntax right first. Then let's see how much of that has helped you, enterprise company. And then let's see what else you need that is still practical, right? Now, for me, I'm okay with catering to these large enterprise companies for a couple reasons. One, that's more Go jobs. more projects. That's whether you want to be full-time, contractor, trainers, it just brings more opportunity into the ecosystem. So if generics is going to bring in another 1,000, 5,000, 10,000 of these big companies, then I'd rather us as a community really buckle down and try to get this as right as we can to bring all that opportunity in. So those companies, they're going to, at some level, abuse generics because that's why they're coming in, right? So we're going to still see some of that regardless, because that's the mindset of a certain set of developers building a certain set of apps, and I'm okay with it, right? But I think the documentation sanctioned and stamped by the Go team is going to be our biggest friend here to stop it.
Yeah, I think it's a great answer. And also Jessica on the chat said documentation for the win, 100%. So it's good agreement there as well. So you've obviously been working with it for a little bit. So somebody's asked, are you actually a fan of generics? This might be a question you can't answer or you don't want to answer, but maybe if you can't answer whether you're a fan or not a fan, what excites you and what kind of worries you most about the
I'm upfront and honest with everybody. I'm a fan of generics because I have a consulting contracting company, and that could bring another 10 clients in overnight, right? Why is Bill Kennedy, this is the 40th time I've given this talk. I'm writing all about it. Let's be upfront and honest. Why am I doing it? Because in a year from now, when this hits the language and the big enterprise companies start Googling Golang generics, I want to be an expert in this space. I want to know this stuff. I want them to come to me and say, Bill, we need help, right? So I'm a huge fan of this because of the opportunity it brings. I worked in C++ and C#. I never used generics. I stayed away from it. When people on my team used it in their code, I told them I'm not maintaining that code ever. Don't even come to me. I don't exist, all right? So this isn't something I'm necessarily going to be using or necessarily promoting unless it's going to give us the best form of readability, code comprehension, and maintainability. And trust me, I mean, I'm going to be sleeping on that before I just, say, yes, let's do it. But I am a huge fan of this because of the opportunity that it's going to bring to Go and everybody that's here.
Sure, thanks. Thank you. Yeah, great. Well, we've got loads of comments saying thank you very much. It's been a great overview. So I think I think it's for me as well. It's just been a kind of jump start into the review and a really great overview. So thank you very much for that.
Yep, and just if you go through the repo and you have questions, just send me an email. I'm sure you can find my email on my Twitter account. You can find me all out there. Don't ever hesitate to send me an email. I'll do my best to get you answers to anything that you have.
Awesome, thanks very much, Bill. And yeah, the draft documents, the talk material, all of that kind of code, it's all linked in the chat, and it's also linked in the YouTube chat. And we'll pop it over in Slack as well, in the Slack channel, so you can access that, because it's exactly the kind of thing you want to, afterwards you want to go and have a little look through later on and kind of refresh yourself. So yeah, that's I'm definitely going to be doing that. I'm on a train a bit tomorrow, so I'm going to be definitely looking at that. So just a reminder as well that our raffle is open. That's on at gophers.london/raffle, and the code is spooky, and that's of course our regular raffle to win JetBrains licenses, which is a really good prize. And another mention for our sponsor JFrog. They're our sponsor for 2020, and they've been sponsoring us through this really weird situation that we all find ourselves in. So we really appreciate that. Appreciate the support at this time. So if you would like to either scan the QR code, if you've got your QR code reader ready from the previous mention, or you can also go to bit.ly/LondonGoJFrog t-shirts, and you can enter a draw to win a t-shirt there. So the next meetup, assuming we're going to be online again, the next meetup is planned to be November the 18th, and then the meetup after that is December the 16th. But we'd also like to ask you, the community, what is working for you at the moment. We appreciate that we can't have our in-person meetups at the moment. And we're still trying to think about how we can kind of bring those back safely. And also we're kind of conscious that that's a real driver, or was a real kind of draw to the meetups, that, you kind of get to see friends, you get to make new friends, you get to have pizza, you get to have beer, and it's a bit of an event. So, Zoom might be, or online might be a bit of a kind of not such a good alternative. But we'd really like to hear from you about what you think and what you prefer. If you want to just drop us a line, you can get us on Slack. You can reach out to us on the web. But also we'll try and contact you as well. We're trying to get some elicit some feedback. So anyway, next meetup on the 18th. Well, thank you very much for joining us as well. And thank you again to our sponsors, Tyke, JFrog and GoBridge. It's been another Zoom meetup, but we think a really good one as well. So as ever, the talk will be up on YouTube, and you can watch it on repeat then. So you can go back and refresh yourself. Great. And thanks, just a final thanks again to Bill. Fantastic talk, and thank you everyone for joining us.
Bye everyone, thanks.